Okay, geometry students, we're going to take a little bit of time before we get going on the assignment to look at the calculations on the examples from the notes for surface areas of composite solids. I apologize for not being here today. This is a really bad day for me to miss, given the difficulty of the calculations that you're going to have to be doing. So I'm hoping to get you enough information to at least get you started today, and then I should be back in class on Wednesday, and we can finish up whatever questions you may have regarding the assignment. So please follow along with the examples, and then you'll get your assignment, your worksheet, and then you can get going. Okay, our objective for the day is to learn to describe composite solids, then calculate their surface areas. Okay. Now, it may seem a little bit strange that part of the objective was to learn to describe surface areas for composite solids or describe the composite solids, because you may be saying, well, we already did that when we were talking about volume. And true enough, we did do that when talking about volume. When it comes down to surface area, the description changes somewhat depending on what the solid is doing. So when calculating surface areas of composite solids, the same ideas we used with volume still apply, but you will see that there are some new considerations, and we're going to be looking at the same 5 composite solids that we looked at with volume. So let's begin. Okay, we're going to start off with this this tower shape again. Okay, so once again, the shape remains the same, so the description should not be any different than it was before, and the description was, get my computer to keep up with me here, it was a pyramid plus a rectangular prism. This has not changed. But of course, now that we're finding surface area, our formulas change. And remember, for a figure that has one base, like a pyramid, we have a formula: 1/2 times the perimeter of the base times the slant height of the pyramid plus the area of the base. Kind of a complicated formula, but we've seen it before. 1/2 PS plus big B. And the rectangular prism, okay, that was when we defaulted to the net. Okay, so we'll figure out the different pieces of the net, and then we will add them all up to find the surface area of the rectangular prism. Okay, one of the things we did not have to worry about with volume is when we put two figures together, when volume is concerned, nothing is lost because you have one mass and another mass being added together. So you simply get a sum or possibly a difference of two masses. But with surface area, we have another problem. When two figures are pressed together, we lose certain pieces of the solids, or small pieces of a side of the solid. So when we look at the pyramid, let's look. Do we actually get to see all of the different sides of the pyramid? Now, when I say do we get to see them, it's not like, hey, we can't see the backside of the pyramid, so that means it's not there. Of course, it's still there. So the pyramid still has its 4 lateral faces. But the question is, what about its base? Now, its base is a consideration for the formula, but its base is not actually exposed to the exterior of the solid. So we would not actually want to consider the base of the pyramid as far as surface area is concerned, because it's not on the surface. Okay, and how about the prism underneath it? Okay, the prism underneath it, if we are considering the top and the bottom of this prism to be its bases, well, what about the base that's up on top that the pyramid is sitting on? It's no longer exposed to the outside of the solid. So we would not want to consider one of those bases. So we're going to have to make some adjustments. For the pyramid, we're looking for the lateral area only, which means the base is not needed. We would actually remove that from the formula. And the rectangular prism, we would not need one of its bases. Okay, so let's see if we can figure out what the surface area formula for this particular situation is actually going to do. Our surface area is going to equal, okay, we said 1/2 times the perimeter times the slant height, but the base has been removed from consideration because it's not exposed on the solid. Okay, and on the rectangular prism, okay, let's see what we have here. Okay, all this is going to be added up, the pyramid plus the prism. Okay, on the prism, we have the base that's on the bottom. It is square, so we have that 6 squared that is on the bottom. Okay, and then we have the 4 lateral faces, these big rectangles that are running lengthways from top to bottom. Okay, we have all of them are 6 by 7 rectangles, so there's actually 4 of them, and they are 6 by 7. Okay, so this is actually what our formula is trying to look like once we get our values plugged in for our pyramid. Okay, so how about the perimeter of the base of the pyramid? Well, it's 6 units on each side, and there are 4 sides like that. So there's the perimeter of our base, 4 times 6. And we need to know the slant height of the lateral face. Okay, well, having a hard time visualizing this thing, so what I'm going to do is I'm going to pull out one of these triangles. Okay, chances are you're probably envisioning slant height right about there, okay, on that side. Okay, so let's see what we know about this. We got 6 across the bottom, okay, and let's see what else we've got. Don't have any other information about this triangle other than inside of the pyramid. We can probably figure out what's going on with the height inside of there. Okay, now the height inside of there, let's see what we know. We know that on this measurement right there, we have 7 units. Okay, and the overall measurement is 11. That means there must be 4 units left over for the overall height. Okay, so as it turns out, I don't really need this triangle that showed one of the lateral faces. What I really need is that triangle from inside of the pyramid, okay, where we have the slant height that is not known, we have the overall height that is 4, and if we could figure out what is going on with this little guy right there, we'd be good to go as far as Pythagorean theorem is concerned. Okay, and we have 6 units all the way across the edge of the base there. And of course, this little triangle that we've got built in there using the height, he only goes halfway across, so the apothem is 3. Now, hopefully you can see right off the bat that the slant height is going to be a 5. Now, if you can't see that, okay, it's probably time that you learn the 3, 4, 5 right triangle, but if you must, plug it in to Pythagorean theorem. We know the 2 legs, 3 and 4. That's 9, 16. So you end up with 25 equals s squared, and when you take the square root of both sides, there is your 5. Okay, so our 5 comes from there. Hopefully you've just got the 3, 4, 5 special right triangle or Pythagorean triple memorized by now. And then over here, we've got some calculations going on. So let's start cleaning this up a little bit. 6 squared is 36. Okay. And 4 times 6 times 7 is 42. Okay, still cleaning up the calculations a little bit. Inside of the parentheses there, 4 times 6 is 24. Okay, times 5, and we got 1/2. Okay, so we've got a good bit of numbers going on here, so I'm going to go ahead and pull the calculator up, and let's have a look at what's going on here. Okay, so in this lateral surface area of the pyramid, we have 1/2, which is then multiplied by 24, that's 4 times 6, and then multiplied by 5 also, that is 60. And then on the right side, we have 36, which is being added to 4 times 42. Make sure you get your order of operations right when you go through that calculation. And I get 204. Okay, so we have 60 units on the lateral surface area of the pyramid. We've got 204 units on the prism, everything except for one of the bases. And that makes our calculation 264, and then whatever the units are, which were yards in this case. Remember, surface area is second dimensional. Okay, so as you can see, there's a good bit more to think about and pay attention to as far as surface area is concerned. Okay, so let's take a look at the next one. All right, this shape is the same as it was before. It is a cylinder and a cone. Okay, so formulas for this guy. A cylinder is a special kind of a prism, and with prisms we look at the net. Okay, so we're going to look at the net of the cylinder, and then a cone is a special type of a pyramid, so we will use the 1/2 PS plus big B formula. Okay, now let's think about what's actually exposed as far as surface area is concerned. Now with the cylinder, clearly we can see one of the circular bases. Clearly the lateral face, the rectangle, is exposed, but one of the circular bases is being blocked by the cone. So we would want to remove one of the bases from the net of our cylinder. On the cone, well, we already talked about the cone is blocking out the circular base of the cylinder, so that means the reverse must be true as well. The cylinder is blocking out the base of the cone, so we would only be looking at the lateral area of the cone. Okay, so our surface area is going to look something like this. Okay, our cylinder is going to have one circular base, pi r squared. And then it is also going to have a rectangle that's wrapped around this cylinder. And if you remember, the dimensions of the rectangle are the circumference of its base, which is 2 pi r, and then that is multiplied by the height of the rectangle, which is the height of the prism. Okay, so there is your cylinder. We've got one base and the rectangle wrapped around it. Okay, look back at your notes on finding surface area of a cylinder if you're having trouble following that formula. And then out of the cone formula, we do not need the base since it's being blocked by the cylinder. So 1/2 PS. Okay, let's see what we can plug in here. Okay, we have pi. We need the radius of our cylinder, which is half of our diameter, so it's 3. So pi 3 squared plus 2 pi. The radius again is 3, and that's going to multiply by the height of our cylinder, which is 2. Okay, so no worries there getting the information plugged in. And over here, we have 1/2 times the perimeter of the base. Now remember, our base is a circle. Perimeter is found by 2 pi r. So that's 2 pi times the radius, which is 3. And then the slant height of our cone. Okay, well, that one's not marked for us in the picture. Okay, but basically, there it is in there. We need the slant height. We know for a fact that the radius is 3. If we could find the height of this pyramid, that would set us up for Pythagorean theorem. So let's see what we know. All right, well, on this measurement up here, 5 feet, 2 of the feet are used up by the height of the pyramid. That means 3 feet are left over for the height of the pyramid. Okay, so we have 3 units on the radius, we have 3 units on the height. We need to know the slant height. Okay, well, this one's not going to turn out quite as nice as the previous example did, but still not too tough. Just working out Pythagorean theorem. And then to get the squared off of the s, we take the square root of both sides. Okay, now I'm not going to worry about this decimal point. I've been telling y'all we try not to round off in the middle of the problem if we can help it. Well, the easiest way not to round off in the middle of the problem is not to end up with a decimal point in the first place. So I'm just going to take this value, square root of 18, and I'm going to plug it directly into the formula. That way we don't have to worry about losing any decimal points. Okay, so let's see if we can clean this up a little bit. Okay, here at the beginning we have 3 squared, which is 9, and of course the pi is still there, so we have 9 pi. Plus, we have pi again in the next term. 2 times 3 is 6, times another 2 is 12. So we've got 9 pi plus 12 pi, and then that is added to down here, just combining some terms. 1/2 times 2 is 1, times 3 is 3. The pi is still there, and square root of 18 is still there. So all I've done is just combined and simplified some of the basic coefficients. Now I'm going to go to the calculator and get a little help here. Okay, so we have 9 pi, and then also added to 12 pi, so we actually could have just said 21 pi and plugged it in, and we end up with an answer in the ballpark of 65.97. Then we are going to add to that 3 pi times the square root of 18. Oops, I've got a problem there. Let me retype that. 3 pi times the square root of 18. That looks a little better. And we've got an answer just short of 40. Okay, so if I combine these two decimal points, should be good to go. I'm just going to use those decimal points from up at the top of the screen, 9734457 trying not to round off until I get to the answer. And it looks like we have an answer, a surface area of 105.96, and then whatever our units of measure are will be in the second dimension, square feet. Okay, let's look at the next one. Shape description, just as it was before, this is 2 rectangular prisms. Okay, so we say we got 2 rectangular prisms. Based upon the information we are given, we would be left to assume that the large rectangular prism is a cube, since they did not give us any other information. Okay, so on surface area for a cube, we are looking at 6 squares that are identical, so 6 times an edge or a side length squared. And then, of course, the other rectangular prism would be the net. Okay, so technically what we're looking at is 2 nets. Okay. Let's see, on the large rectangular prism or the cube, nothing is being blocked or anything like that. However, we are missing 2 small little rectangles where this rectangular prism on the inside has exited from the cube. So we will have to remove those 2 little rectangles from the overall surface area. However, we have some new surfaces that are created by the cavity that the small rectangular prism has created. Okay, so notice on the formula up top and the formula we're looking at now, this is an addition problem. We have a rectangular prism plus another rectangular prism. Okay, with volume, we would have subtracted one from the other because the little guy took away from the big guy. But when it comes to surface area, having one take away when volume is concerned actually causes one to add to the other where surface area is concerned. Okay, so on the little rectangular prism, we have these new long rectangles moving through our larger prism that were not there before. So we've got to count those. However, the bases of this new little rectangular prism that's passing through the middle, okay, he doesn't have any bases. This is open to the kind of the external air of the figure. So we're actually only looking at the lateral area. Okay, so the rectangular prism, the big one, we have to take away the 2 rectangles where the small prism exits. And for the small prism, we only want its long rectangular lateral faces, not the rectangular bases in this case. Okay, so let's see if we can figure out what on earth all that means. Okay, now what we have here, as we said, we're going to have to assume that this larger prism is a cube. That means we have 6 sides, and each of them is side squared. However, we need to remove the base and the height of the little prism. Okay, so we'll fill that in here in just a moment. Then to that, we are going to add just the lateral faces of the small prism that's in there. Okay, well, looking at the faces or the lateral faces of the small prism, we have two different sizes in there. We have two guys that are base times height, and then we have two other guys that also have base times height, but they don't have the same dimensions. Let's fill in that information before this gets too confusing. Okay, 6 sides on our cube that are 7 units long each. So 6 sides at 7 times 7. We need to remove from that this little bitty rectangle that's sitting right in there that the small prism kind of knocked out of our big prism. So that's the 3 times 4 that I put down on B times H from above. Okay, now looking into the prism, let's finish this stuff off here. 2 times, we have like this rectangle right in there. Okay. We have 2 like him, and he is 3 units times 7 units. Okay, but then we have 2 other rectangles that are like this guy, and he is 4 times 7. So that's how come we did the 2 different measurements inside of that last set of parentheses there. Okay, 2 of one size lateral face, the 3 by 7, and then 2 of a different size lateral face at 4 by 7. Okay, so if you can get to the numbers, in a lot of cases this is not terribly difficult math. Let's just clean it up a little bit, see what we have here. Okay, 7 squared is 49, 3 times 4 is 12. Try not to lose your parentheses as you move through the problem. It'll help you keep from getting your order of operations really messed up here. 3 times 7 is 21, and 4 times 7 is 28. We can even clean this up a little bit more if you want to. Okay, but it's completely up to you. At some point in time, we're going to need to get the calculator involved, and for most of you, it's probably right about now. What's 6 times 49? That's 294. And then, of course, you have minus 12 plus 2 times 21 is 42, and 2 times 28 is 56. Okay, we ought to be able to get it from here. Now we're all the way down to addition and subtraction. On the left, we have 294, take away 12. On the right, we have 42 and 56. And then those two values are supposed to be added together. And unless I've done any typoed anything along the way, it looks like our surface area is 338, and we're talking square inches. Next, okay, we had the triangular prism and the hemisphere. Now, of course, it's still a triangular prism and a hemisphere. They're going to be added together. Okay, putting them together created additional surface area, so it is an addition problem. On the triangular prism, we have everything about the triangular prism exposed except for the area where the hemisphere makes contact with it. So we are going to have to remove that circular area where they are touching. Okay, and on the hemisphere, of course, we have a formula for the entire surface area of an entire sphere, but we're only looking at a hemisphere, so we only want half of that. So we will take 1/2 of 4 pi r squared. Okay. Oh, I'm sorry, I got a little ahead of where I was on the screen. Okay, so we're looking at the net of the triangular prism plus 1/2 4 pi r squared. Okay, on the triangular prism, we have to remove that circle where the hemisphere makes contact, and then there is no adjustment on the hemisphere other than to take half of the formula. So let's take a look at what we have. For the triangular prism, looking at the net, okay, we're going to have one triangle. So we're going to have a 1/2 times base times height. That's our triangle. Then we're going to have to add to that 3 rectangles for our lateral faces. And then from that, we have to take away where the hemisphere makes contact. So our formula actually looks like this: 1 triangle plus 3 rectangles minus 1 circle. And then, of course, we have plus 1/2 of 4 pi r squared. Okay, so let's see if we can plug some numbers in here. The triangular base. Okay, let's pull that triangular base off of there. The problem did tell us it has a regular base. Okay, so there's our triangular base. And if you remember what I told you about your isosceles triangle here, you have all kinds of rules that are in play. You can absolutely do Pythagorean theorem, okay, from there, or you can simply memorize the 30, 60, 90 triangles, which means the long leg is going to be whatever the short leg is times the square root of 3. Okay, so that's kind of getting to be old news by now. So let's plug in our information here. 1/2 times the base of the base is 8 times the height of the base is 4 root 3. And again, I'm not going to change that radical into a decimal point just yet. I don't want to round off until I get to the end of the problem, so I'm going to leave that as a radical. We have 3 rectangles that are all the same size traveling around our triangular prism, and they are all 8 by 11. From that, we have to subtract pi times the radius of that hemisphere where it's touching our prism. Okay, well, let's see. We do not have the radius, but we do have a volume of 100 cubic centimeters. So let's see what we have. They talk about volume. Volume is 4/3 pi r cubed, and they say the volume is 100. Well, we need to know what that radius is, so we need to get that thing out of there. All right, so let's see what we can do here. If we take the problem, we want to get rid of that 4/3. We can multiply by the reciprocal. Okay, whatever we do to one side, we have to do to the other. That will cause the 3 in the numerator and the 3 in the denominator to cancel, the 4 in the numerator, the 4 in the denominator to cancel. And let's look and see what we have going on with this value. We have 100, which is multiplied by 3, but divided by 4. We have 75 on the left side of the problem here. Okay, and from there, I need a little extra space on my screen here, so let me open this up a little bit. We have pi is multiplying times our radius cubed, so that would be the next logical step, divide by pi. That will cause pi to cancel there. Okay, so let's see what's going on with the numbers from that. We have 75, which is divided by pi. Okay, so we have a number in the ballpark of 23.87. And what we need to do now is we need to get that cubed off of our radius. Okay, so the only thing that can undo something being cubed is the opposite of cubed, and that is cube root. So we're going to take the cube root of both sides. And once again, cube root is a calculation our calculator can help us with. It's in the math menu. Okay, so when you hit the math menu, it pulls up this. And as you can see, option number 4 right there is cube root. Okay, so select it, and the calculator wants to know what the cube root of, well, I'm going to use this 23.87324 number, so I'm just going to hit second answer. And it'll pull up that number, including all of its decimal points, and give me a radius. Okay, so we have a radius right in the ballpark of 2.88. Okay, now all of that work was done so that we could plug in back here for the radius. It was 2.88 squared. Okay, that was a lot of work, but we had to do it because we needed the radius, and we actually are going to need it again. 1/2 times 4 times pi times, I'm out of space, but 2.88 squared. Okay, we got a lot of numbers going on here. Don't freak out about it. They're all manageable numbers. Let's see what we have here. Okay, in this first set of parentheses, we have 8 times 4 is 32, and half of that is 16. There's that square root of 3 still hanging on. Let's see what we got going on there. That's a little tougher calculation. 8 times 11 times 3, that is 264. And then from that, we have to subtract 2.88 squared times pi. And we've got something in the neighborhood of 26.06. There's that first calculation, the triangular prism minus where the hemisphere is touching it. Okay, and then on the hemisphere itself, we have 2.88 squared. We have half of that times 4 times pi. A lot of numbers going on. For those of you that have a habit of skipping steps, this is going to be trouble for you. You probably better learn to start writing some things down rather than skipping steps. And let's see what we have here now. 16 square root of 3 plus 264 minus 26.06 plus 52.12. And unless I've made any mistakes along the way, we have a surface area in the ballpark of 317.77. And then our units of measure were what? Centimeters squared. As you can see, some of the calculations are really pretty straightforward. Some of them are a lot more in depth. There's just extra information to take into account, but that's why I've been telling you the volume did not hold a candle to the calculations the surface area was going to make us do. Just one more. Okay, and that was this guy. Okay, this time we have a cavity inside of our solid. Okay, so that is actually going to increase our surface area because there's extra sides exposed. So this is a cube plus a pyramid. Okay, so the formula for finding the surface area of a cube is, again, 6 sides that are all squares. So 6 times side squared. And then a pyramid's formula is 1/2 times PS plus big B. Okay, adjusting the formulas from there are only 5 sides of this cube that are still part of the solid, so we would want to remove one of those sides. And then on the pyramid, the lateral faces are all exposed inside of this cube, but the base is missing. Okay, so lateral area only. All right, so adjusting the formulas, we would have only 5 sides of our cube, so that's easy enough, 5 s squareds instead of 6. And then, of course, adjusting the pyramid's formula, we just take the plus b off because the base was not part of the problem. Okay, so let's see what we've got here. All right, S in the case of the cube is the side measurement, so that is 23, which needs to be squared. And then we have 1/2 times the perimeter of the base. Well, that's easy enough. We have 4 sides that are 23 units each traveling around the perimeter of the pyramid. And then S in this case is the slant height. Okay, so slant height would be maybe something like that guy inside of there. Now the overall height of the pyramid would be there. So let's see what we actually have in that triangle. We have slant height out there. The overall height is 23, okay, of the cube and the pyramid. And then the apothem inside of there would be half of 23, which is 11 and a half, or 11.5. Okay, so we got some kind of crazy numbers going on inside of that triangle, but it's still just Pythagorean theorem. Let's see what we have going on. 11.5 squared, not familiar with that number. It's 132.25. We also have 23 squared, which is going to be 529. Okay, so 529 plus 132 and a fourth. We have 661.25, and that is equal to the slant height squared. Of course, we don't want the slant height squared, we just want the slant height, so we'll take the square root of both sides. Okay, and let's see what that number is. Okay, we've got a number that is in the ballpark of 25.71. Okay, well, that is our slant height, which belongs in the problem back there. Okay. From here, it's just cleaning up the math. We've already seen that 23 squared was 529, but if you didn't catch that or remember it, you could always calculate it again. And then let's see what this number is over on the right. We've got 1/2 times 4 times 23 times 25.71. Okay, so 1182.66. And then we need 5 times 529 on the left side of the problem. And to that, we need to add 1182.66. And we end up with a surface area of 3827.66, unless I have done something wrong somewhere, which is possible. I do not have these answers written down, so I have been working these and talking about them and typing them in all at the same time. So if I've made an error somewhere and somebody has been aware of it, please point it out to the rest of the class. Okay, and I apologize for the length of the demonstration here, but as you can see, these are complicated calculations, and this is going to take us some brain time. Okay, so at this point in time, the substitute's going to pass out the worksheet for you. I want you to get started while this is fresh in your head. I know you've only got about 10 minutes left in class, but get started on it and take it home as well and work at least a couple of problems. I want you to come back to class tomorrow with at least 2 of the 5 problems completed, and then that'll leave you 3 of them for you to work on in class and ask questions and all that kind of stuff, and hopefully that'll mean you won't have any homework left over at the end of the day tomorrow. Anyway, I appreciate your attention, and let's see if you can't get some work done.